Anyway, thanks to the organizers. It's certainly a pleasure to speak at this birthday conference for Mladen. Following Karen, I've got a picture. Whoops, there it is. Anyway, so it's certainly been one of the great pleasures, privileges in my life to think about mathematics with Mladen. This to me always struck me as a good, maybe an album cover or something.
Hard at work here.
Hard at work. There's a constant theme here. And I think this is in Marseille. I think the other picture was here, maybe the same sunglasses. I don't know. Anyway, so that's the end of the pictures. And what I'm going to talk about is a long-term project with Michael Handel. We've put up a preprint on the archive within the past few weeks. And this can be viewed as a probably direct outgrowth of the work Karen mentioned that from the Institute when Michael and Mladen started thinking about out-FN. So I'm happy to talk about this here. So let me put up my notes. Okay, so Karen taught me that you have to put up a goal. And that's so you can tell later if it was a tragedy or a comedy. And the goal is so the conjugacy problem, to solve a conjugacy problem, you need to produce an algorithm. So the goal is to describe the algorithm. And let's start with an example that will probably follow throughout. So here's an example of an outer automorphism. So here's a rose whose fundamental group has been a graph whose fundamental, it's a rose whose fundamental group has been identified with the free group. And to represent an outer automorphism, we need a homotopy equivalence. And this one is very simple. A is fixed by F, and B maps to BA, and C maps to CB. Okay. And there are some features that you're supposed to notice. So the first feature is that every outer automorphism is represented by, as Karen mentioned this, by a homotopy equivalence of a marked graph. So every phi in out-FN is represented by such a thing, such an F from G to G. And, oops. Another feature is that this one is sort of special in that if you iterate an element under F, it grows polynomially. So for example, if the C wasn't there, if it was just A, suppose we just had the single loop A, then that would be fixed. A would be fixed, would have constant growth. And then suppose we didn't have the C, we just had A and B. Well, B maps to BA, so if you iterate B, well, B goes to BA, goes to BA, goes to, you can see it just picks up an A every time. So that's linear growth. And if you, with the C, if you iterate the C, well, C goes to CB, which goes to CB, BA, CB, BA, BA squared. The next time you have BA cubed, BA to the fourth. And this is, so this is growing linearly, and this is growing quadratically. So this particular example grows quadratically, and in this talk we're interested in elements of out Fn that grow polynomially. So we're interested in polynomial growth, like in this example. And there's another feature of this example I want to focus on, and that's that the graph G is a union of edges, E1, E2, dot, 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 finite union of edges, and F of any edge, EI, is EI followed by a suffix. So the suffix of A is trivial, the suffix of B is A, the suffix of C is B. And the UI lies in what you already understand. So UI is in E1 up to EI minus 1. Okay, so an edge goes to itself times something lower. And so for the purpose of this talk, something with this property, something like this is going to be called a CT, i.e. F from G to G is a CT. So T is for train track, if you're familiar with those things, but we're just going to focus on things with this very, very simple type. So an actual CT has more properties than this, but for the purpose of this talk, this is the essential feature. And anything of this form will have polynomial growth. Okay, and in fact, something that has this form, by definition, i.e. the automorphism, outer automorphism represented by F is in this set UPG. So for us, UPG, the PG stands for polynomially growing. U is something with this special type. So the set of things that can be so represented is UPG, and we're interested in the conjugacy problem for UPG and out Fn. In other words, if somebody hands you two elements of UPG, can you tell if there's an element in out Fn that conjugates one to the other? That's the problem. And the difference between UPG and PG is you're supposed to think of as not being very great. In fact, any element in UPG has a positive power. Sorry, I said that backwards. Any polynomially growth, any polynomially growing outer automorphism has a power, positive power in this set. So if you're willing to take powers to get rid of some kind of periodic behavior, you can take any polynomially growing guy and get it into UPG by taking a power. Okay, and the theorem of the title, which is joint with Michael, is that there is an algorithm. It has input two outer automorphisms in UPG. This is always UPG of Fn. And it has output. Well, yes, this is if there exists an element of out Fn conjugating phi to c. So this is what we mean by saying theta conjugates phi to c. So for the rest of the talk, phi and c will be two elements of UPG, and we'll be looking for a conjugator, theta. And it outputs no if there doesn't exist such a theta. And further, if yes, theta is produced, some theta is produced. So that's what's meant by the title. I don't know how to manage these. Is there a, how do you reach the top one? Or is there a button?
On the right.
Oh, okay. Okay, and then there's some history to the conjugacy problem. For out Fn. So there's sort of two sides. One is the polynomially growing side, like we're studying here, where every element, where under your the elements you're considering, every conjugacy class grows polynomially like this. And so what's been done in the polynomially growing case? Well, there's the sort of linear version of UPG. Like this, but with linear growth. And this was settled by Cohen and Lustig. And I think the year was publication year is 99. And then there's the linear case where you allow rotation, so general linearly growing outer automorphisms. And that's Kristich, Lustig, and Voigtman. And I think that was 01. And then there's the other side of things where you have exponential growth. All the elements except for the trivial element grow exponentially when you iterate. And there's a bunch of names, and since that's not the focus of the talk, I'll just list the names. So Sella and Los and Lustig and Damani are the, you can look up their works. And then there's, for the general situation, Martin Lustig has some preprints around 2000, I think, and but these never published, I guess. So What was the question? Well, what?
It's not a result. It's not validation. It's not a result.
Okay, well. Yes. I don't know. These are, we found, I don't know, I'm just trying to be professional here. Yeah, right. This is part of the history. Okay, so now I would like to, how many minutes? You're not flashing anything.
1 minute.
Okay, so now I would like to start talking about some tools for working on these problems from a train track point of view. And one tool is something we call the eigengraph. So always for us, so let me write that. So for the rest of the talk, I mentioned how phi and c were in UPG, and F is going to denote a CT for phi, and G is going to denote a CT for C. So if those symbols appear, you'll know what I'm talking about. And so one key tool is something called and I already wrote it, the eigengraph. So given a CT, you can write down what we call its eigengraph, and it starts like this. So you first start with fixed edges and vertices. In the example, there's only one vertex, it's fixed, and there's one edge, it's A, that's fixed. So at this point, you would get just that. So that's what we're building up the eigengraph, and that's what we have so far. The next thing you do, well, you do something for the linear edges. So then you add a lollipop. Did I spell it? For each linear edge. So I don't know, this word I think is familiar, but it's, those kids suck on lollipops. So here the linear edge is B, and so what you do is you add on, we're going to add on an edge B, and then we're also going to add on its suffix like this. So this is the lollipop corresponding to the edge B. And so when we add that in, we'll get an edge labeled B together with its suffix. So this is what we have so far. So far we've got something from the fixed edges and the linear edges. And if I were to stop here, you might notice that this records the fixed subgroups or fixed conjugacy classes. If you take any loop you can write in here and hit it with phi, it's fixed. So this is an easy way to quickly record sort of some fixed data of your outer automorphism. And then finally, to finish, for the other edges, so remaining edges, for each remaining edge, you add a ray. So let's call this edge E. Remaining edge E, you add the ray R sub E. And what's the ray R sub E? Well, you've we sort of saw it developing over here. So C is developing a ray, so that the infinite ray would be C, B, BA, BA squared, BA cubed in that case. And more generally, EE is defined to be E times its suffix times F of the suffix times F squared of the suffix, etc. So that's an infinite ray. And if we add that, in this case, we'll add on the ray R sub C, and it starts with a C, and then it goes C, B, BA, BA squared, BA cubed. Okay. And so that's the eigengraph. This construction works for any CT. And what you're supposed to notice now is the object that you have records fixed lines. So not just fixed conjugacy classes, but fixed lines. If you draw any line in this object, you know, immersed line, it will be fixed by your phi. So this is recording not just fixed conjugacy classes, but fixed lines. And that's a very important object for us. Why? Okay, so let's just make sure I'm following my notes here. Okay, so there's an older result with Michael we call the recognition theorem. And so we're using that notation phi and c. Okay, so phi and c are conjugate, conjugate, if and only if there's a theta in out Fn such with two properties. One property is if you look at the lines in the eigengraph for F and compare that to the set of lines in the eigengraph for G, theta has to induce a bijection between them. So it's pretty clear if you think about this, because you can see that the eigengraph, the lines carried by it, that's an invariant of the outer automorphism. If they're conjugate, theta better do this. But in fact, that's enough with one extra condition. So this and one other condition, and it's an easily checked numerical condition that we're going to ignore because we just muddy the talk, and it's not a big feature. Okay.
Can you remind us what you mean by lines? You just mean these rays?
No, a ray is a half line. A line is an what you sort of think it is. So I'm going to, a line will begin and end at a ray. In this case, there's only one ray. So it's an immersed, properly immersed line in this picture. So the line would sort of start at an end. It's immersed. It'll wrap around the graph in an immersed fashion. And then it has to end up going back along a ray. The more general, of course, graph can have many components. It can have many rays. But this is just, this is sort of the simplest possible example of quadratic growth. So something that occurs, say, in out Fn that wouldn't occur in the mapping class groups. And yet, you know, it's so simple, but there are a number of interesting features, and that's what we're focusing on. Okay, and what we're going to try to do, there's some other tools I'm going to tell you about now. And so in order to use those other tools, what we really want to do is take this condition that lines go to lines. You know, these rays can be quite complicated, and the lines can be quite complicated. So there's no clear way to express, you know, a line goes to a line, say in a simple algebraic fashion. So what we want to do is try to say, you know, translate this condition into algebra as best we can, and then see how far we get, and then see what extra work is to be done. Any questions at this point? Okay, so the thing that's going to take care of the algebra for us is Whitehead, and in the linear conjugacy problem, Whitehead plays a big role. So let me tell you about that. So this what I'm about to, we'll call W for Whitehead, and a model Whitehead, in this case, Gersten statement goes something like this. So there exists an algorithm with input, in this case, say H and K, which are two finitely generated FG, finitely generated subgroups of Fn, and output, yes, this is if there's a theta in out Fn conjugating phi to c, conjugating, well, theta of the conjugacy class of H equals the conjugacy class of K, and no, if there doesn't exist such a theta, and there's always further, if yes, theta is produced, and further also, for, whether or not such a theta exists, further a finite presentation for the stabilizer of, say, H, for the set of all theta in out Fn that takes, say, H to H. Okay, you get a finite presentation for that. So this is usually, this is a McCool type statement, and we're going to use this kind of thing. So if possible, we'd like to encode invariants as conjugacy classes of subgroups, and if we have such an invariant, then theta better preserve the invariant. So this Whitehead result should be handy. And the next oh, you can't do two at once? And then the next thing here is just a simple lemma, but it kind of gives the spirit of how to proceed. So this is going to be called R for reduction. So lemma. Suppose you have a subgroup of out Fn. And suppose it has finitely many cosets. So this may be infinite index. It usually is if you're in an interesting situation. But suppose you're told that there are finitely many cosets. Let's call them chi theta 1, chi theta 2, such that every conjugator, any conjugator, so remember phi and c are fixed and we're interested in conjugating, any conjugator is in one of these cosets. Okay, so you're told, somehow you've gotten down to finitely many cosets of some subgroup. So then the following are equivalent. The first thing is that there exists a theta in out Fn conjugating phi to c. And the second is that there exists a theta in this x conjugating some phi I to c, where phi I is just phi conjugated by theta I. So this second thing is just a restatement, really, of the fact that any conjugator is in one of these cosets. And what it allows you to do is, what it allows you to do is, if you identify some algebraic invariants that you can get answers to using Whitehead, this allows you to reduce to the situation where phi and c have the same algebraic invariance, and it reduces the search of a conjugator to somebody that preserves the invariance. So this, you can take 2 minutes to write down the solution here, but the proof, but that's kind of a philosophy. So we're going to keep searching for invariance, and that kind of moves phi, using this we get phi closer and closer to c. They share the same invariance. We reduce the possible set of conjugators to the ones that preserve the invariance, and we see how far we can get. Okay, so what are the some of the obvious invariants that you can look at? So what are the algebraic invariants we care about? So we've identified really what our invariants are. Our invariants are lines in the eigengraph, but they aren't algebraic. But that's kind of the real invariant. And somehow we want to pull out algebraic invariants from these things. Okay, and here's the eigengraph. And one obvious invariant is the core of the eigengraph, right? We said that records the fixed conjugacy classes. That's certainly an algebraic invariant. So that's something that a Whitehead type problem, Whitehead could handle. So one invariant is going to be, I'll write it like this. So this is the eigengraph, and putting brackets around there, we'll look at the core of the eigengraph. That means remove the rays. A finite graph that represents the conjugacy class of a subgroup, or perhaps finitely many subgroups if there are more than one component. And so this is an algebraic invariant. You could plug it into Whitehead. So that's one of the invariants that's easy to handle. Okay, another is let's define G0 so to be the union of the fixed and linear edges. Okay, so in our example, that's just A and B. And that's the set of conjugacy classes that grow linearly. That's an invariant. And so here's an invariant represented as a graph. So that's an example of a conjugacy class of subgroup that is characteristic for phi. Well, that represents a conjugacy class. We'll write it like that. So that's another invariant. What's wrong?
Can you repeat what's G0?
G0, remember G was our graph. And G0 has certain edges that are fixed. They're in here. And they have certain edges that grow linearly. They're in here. That's it. So it's the union of the fixed and linear edges of, G, your CT. Okay. So these are pretty, you might call the first very obvious invariants, and they can be controlled. In other words, you can quickly reduce to the situation where both phi and c have the same finite fixed conjugacy classes and the same elements of linear growth. Okay. And then G, remember, is obtained from G0 by adding edges. And we're going to add, and we can add them in an order. We can add them in an order so that at each point we get, all these graphs as we go along are invariant by F. So their conjugacy class is invariant under the free group. And you can actually do this in a way, this takes some work, so that each of these subgraphs is an invariant. So here we have, so let's call this one G1, and then there's G2, et cetera. So we have G0 in G1 in G, and these all represent conjugacy classes of subgroups. So there's another bunch of invariants. Okay. And for now, we're going to pause, and that's going to be our algebra, what you might call obvious, or this one's not as obvious, but obvious algebraic invariants. And let's see how far we can get. Okay. So G0, so remember how these graphs were built originally. To be a CT, you just throw in one edge at a time. So what I want to do here, start with G0, that's the fixed and linear edges, and then throw in one edge at a time in such a way that each subgraph you create is invariant by F. And that this structure of being a CT would allow that. Because you always, anytime you add in an edge, you can add in the edge as long as the suffix is already there. So this is obtained from this by adding one edge. This is obtained from this by adding one.
So you're not picking edges in particular?
I said you have to be a little careful when you do this. So this is the key property we want, and such exists. in an invariant fashion.
Do you like start with the quadratic edges? Is that what you do?
Well, you don't have to. You can do it a different. You have to add quadratic edges before you add cubic edges, but you could add some cubic edges before you add quadratic edges. Actually, what's really going on here is there are finitely many ways to do this, but since there are only finitely many, that's as good as one by using finite index stuff.
That's invariant under conjugacy.
This is invariant under conjugacy. What you said is invariant under conjugacy, but I really want to also focus on adding only one edge at a time. If I want to go from quadratic, from say linear to quadratic, I might have to add in all the quadratic edges. We want to just do it one at a time. So that's where a little bit of work comes. Okay. I want that down. Whoops, I want that down. Am I doing this right? What did I just do? Stop. Let's see, I have jet lag as an excuse for anything stupid I do. And this one up. No. Okay, this one up. Close enough. Okay, well anyway, you can see how this would now kind of suggest an induction, because where are we? We have G0 in G1, in G2, etc. And each of these is invariant by F. So let's call the restriction F0, F1, F2, etc. And then we have G0 prime and G1 prime and G2 prime. And each of these is invariant by the restriction of the G's, etc. And this also says that if you build up the eigengraphs, so you get these embeddings. And so what you'd like to do is try to find a theta that takes the lines that are in this, the eigengraph for F0 to the eigengraph for G0. And then as you pass from one of these eigengraphs to the next, this is the one without the rays. And as you move along here, you typically add in one ray at a time, and you add in one ray at a time here. So what you'd really like to do is produce thetas using this filtration. I wasted all that moving up and down for that. Okay. So let me show you the strategy then. So define x sub I to be the set of all theta in x. So I didn't say what x is, but it was indicated by the Whitehead result. So as we moved along, we're building up these algebraic invariants. Right now we have the ones indicated by this board, and we're reduced to searching for conjugators that preserve those invariants. So that's what X is. X is the subgroup about Fn that preserves the algebraic invariant. And X sub I then, sorry, X sub I is a subset of this, well, it equals the set of all X in here with the following property. So such that theta takes lines in this subgraph of the eigengraph to lines in the corresponding eigengraph for G. So that's what it's saying here. We want to find thetas that take lines here to lines here. Three? Okay, so the base case is we want to make, we want to say, prove that theta sub 0 is not empty. So, but theta sub 0 is X. So gamma sub 0 is the eigengraph where you removed all the rays, and we said that's controlled algebraically. So, so the base case is done for us. It's algebra. And then so moving up. Okay, so here suppose you have theta I and X sub I, and you want to produce, so want to produce a theta I plus 1 and xi plus 1 from theta I. So such that two things are true. Well, such that theta I restricted to what you've already got and the one you're trying to produce agree. So it's sort of like an extension problem. But these thetas that you're working with are always defined on all of out Fn. Okay. Okay. So what we have to do then is you move from one eigengraph, subgraph to the next, you're adding on array. So what you really want to know is, can you find, so does there exist some element, theta I plus 1, such that theta I plus 1 takes the new ray to the new ray. So that's what you're looking for. The next, you're wondering if you can, extend this map to the next eigengraph, so you have to understand if you can take rays to rays. Okay, so in the next 2 minutes, I just have to, I'm going to tell you something about rays. And then make ending comments. Okay, so remember array. So here's array. C, B, BA, BA squared, BA cubed, etc. And a limit line, L is a limit line of the ray if every finite segment of L appears in R. So what are the limit lines here? Well, there are only two. A infinity, B, A infinity. So that's a line. It starts with A's, then it does a B, and then it ends with A's. Every finite segment here appears somewhere in this line. And the other one is A infinity, all A's. So those are the only two limit lines. And the features, one feature you're supposed to notice is that the limit lines of this ray exist. I guess it got erased. But they exist. So here we're talking about Ri sub 1. We're in R sub C. For instance, both of these things already live in the core. These things already live in G0. So the limit lines of a ray live in what you've already studied. Well, that's bad news. That's bad news because there's nothing we said here that controls limit lines. These thetas that we've produced so far need not take the limit lines that live below to the limit lines that live below. So this strategy is bound to fail. The good news, though, is that you can define an algebraic invariant that takes care of that and removes that obstruction. Okay, so that takes you to the end of the algebraic phase, and then you have to work harder. and so there's another key homomorphism that's defined on all of X into a finitely generated abelian group, infinite, that you have to define in order to finish your study of the rays. And once you've done that, that's the bulk of the real technical part of the paper. And once you've done that, then you can proceed with and complete this strategy. That's it.
Any questions?
What does the centralizer, the UPG element look like?
Yeah, well, that's a good question, and we can say a lot about it, but not. We don't have what would you call a satisfying answer yet. But we should be able to say something very concrete. But yes, yes.
So what's left in terms of deciding whether two elements are conjugate?
So there's this was for UPG. Yeah. So one thing is you have to move up to PG. That shouldn't be hard. But then
UPG from PG. Oh, so UPG from EG.
Okay, but then there's everything. So on one end, all exponential is known. And on the other end, all polynomial, let's say, is known. But there's this whole middle expanse that has both exponential and polynomial growth. Some elements grow polynomially, some elements grow exponentially, and that would be the next thing to consider.
So how much do you use about these McCool subgroups as you're going along? In particular, do you end up solving the relevant conjugacy problem in them as well?
I don't know the answer to that, but we do use the finite presentation quite a bit because we keep on, we keep on adding in algebraic invariants, and that means we need some information about X. And X, then we get a finite presentation from McCool. I don't think we need the presentation really, but we use heavily the finite set of generators. How? Because there are various permutation things going on, and to control them, you're mapping those to finite groups and see how they restrict and things like that. But I don't know if
you don't end up having to decide if things are conjugate in there.
Well, I guess you could say it is. I think just my quick answer is it should be a byproduct. It should be a byproduct of the proof. Yeah, it should be a byproduct of the proof.